Okay, so I got homeworks from all of you. Fantastic. Thank you. Beautiful. Homework one done. In some ways, it feels like the semester's like been going on forever. Uh, Even though we've also hardly met and it's been going on forever. It's just really weird. So yeah, I'm sorry about what COVID has done to our class in terms of like meeting together. But I mean, I got to do what I got to do to take care of myself and you as well. I think you can test positive for a really long time, even though you're not infectious. I don't know. I think that's true. Kind of unnerving, but I'm definitely starting to feel a little bit better. But do I sound kind of like nasally? Do I sound a little? Yeah, cool.
You sound better than you did last week.
Awesome. I feel better than I did last week. So that's good. I like Monday. I know I said this last week. I was like, next Wednesday, we're going to be in person. I had no idea what it would do to me and how much it would take out of me. So anyway, but I think we can count on next Monday being in person. Cool. So yeah, I'll get those homeworks back to you. There's a new homework up. It's homework 2, and all the deets are in world class in the assignment, like the problem numbers, and we might even start on it in class together today, because one of the things I kind of want to change as part of the dynamic of our class is, and I can't do it myself, but it's all the onus I would put on you, that please start a little earlier on the homework so we can talk about it earlier, because on that last assignment, like I will put stuff on assignments that I really want you to ask about, like stuff I'm not going to mention. For example, like Kyle was asking me a question about the one where you had to come up with the linear combination of like 11 and 7. Yeah, that was it, right? That added up to 1. And there's like a slick way to do that. But nobody asked me about that one. And so I spaced on doing it. But that was why I put that problem in there, is like, so that someone would ask and I could show you the nice way to do it instead of just like guessing at it, which is doable, but not optimal at all. And so maybe we'll address that, especially when I get that assignment back to you. So we're like really starting abstract algebra today. Everything else has kind of been just warming up to this and a little bit of refresher of some essential ideas. There was like one more essential idea that we didn't get to review in depth, and it was the equivalence class stuff, but we'll come back to that. So what I figured is, yeah, the end functions. So we're just going to pull from that first section on those last little bits as we need it, as we're moving along, because I just want to get going. So with that said, I've got stuff written up already, right? So let's take a look at these examples that I've got on the board. So the first one, the bottom one, we talked about literally like day 1, right? The symmetries of an equilateral triangle. That was kind of the intro to the course. But let's start with something a little simpler, maybe. It's definitely a little simpler. It's a little bit smaller to look at the size of the examples. So the set S that I have at the top is just really just the powers of the imaginary number I, right? And so when I say I here, I mean I is the square root of -1. One of the first like really mystical mathy things you get to do, and you even get to do it in like grade school, right? It's like, did you all see this in like grade school? Or yeah, so like the first time you see I is amazing, and it's like a little mathematician seed, right? Because it's like, wow, that's really weird, and I can do stuff with it. So that set S is just all the powers of I. And if I put those into a little table, like I did on the right, and do multiplication. So this operation that's in the upper left, this is just standard multiplication. And I'm going to use the modifier standard, because we're going to use multiplication in a more general way about when we talk about things. But this is just your normal, when I say multiply, you know what I mean. PEMDAS, multiply kind of stuff. So in this little table, notice that we've got that 1, and 1 times anything is that same thing. That's not shocking news. None of that is shocking. But then when we start looking at the mixes of the different elements, we get this pretty pattern that emerges from the depths. And there's something we can notice about this besides, oh, okay, cool, I've got this little like multiplication table set up. There is this nice symmetry down the middle, so that if I folded that table across that diagonal, it would identical elements would meet up, right? Do you see what I'm talking about with the symmetry down that diagonal? Yeah. Cool. So that's just a nice simple table, and it's kind of unique in a way. It's got 4 different elements, so we have 4 elements here, and that's going to become important in a little bit. We'll come back to this one, but there's not much more to say about it, except here's an example of a finite set and the way its elements interact under a particular operation. Now, let's pull back to that day 1, where we had this equilateral triangle and we had these different operations. We had rotation. So for this one, I think in class we had rotation counterclockwise. When I worked this table out, it was clockwise rotation, which changes things just a little bit, but it gets all the essential elements. So I've got different rotations about this central point by 120 degrees, multiples of 120 degrees, so that when I do that, the triangle lands back on itself. Does that make sense? Is there any clarification? Okay, awesome. And then we've got these 3 other operations, which were the flips over these various diagonals. So that was flip A. If I flip it over that, this was flip B, and this was flip C. And so those swap 2 opposing corners of the triangle while leaving 1 fixed. And we lost Sydney. I hope she comes back. Then we looked at, and this actually took a little while, the way those various operations interacted. So now check this out. First off, what is the operation here? So in the top one, it was multiplication. What's the operation here? And there's lots of words you could use for it, but I'd like you to maybe tell me what you think it is. It's not multiplication, because I'm not multiplying a flip times a rotation. How could we think about this?
Is it a composition?
Oh, that's beautiful. It's a composition. Absolutely. You can think of each one of these as kind of a function, and it takes the original triangle and produces a new triangle. So each one of those operations is kind of a function. You can also think of it as an action on the set of points in the triangle. That's another nice way. But either way, yeah, that's it, Sydney. This is composition here. And usually in these tables, this is the first thing. This is the first thing we do, and then this is the second up here. And really that depends on the context. You got to be sure. It's not always that way. So you want to make sure you understand the context of these tables when you look at them. And I don't want to go deeply into this, but is there any quality that the top one possesses that this bottom one doesn't? They're very different beasts. It's freaking huge. Besides, it's freaking huge. 50% bigger or something. Does it have that symmetry across the diagonal? So Kyle's like making a tiny head movement there. No, it doesn't. So check it out. If we go down this diagonal, and it's hard because it's a sloppy table, right? So it's challenging to kind of pick it out. But notice that this element here is not identical to its mirror image across that diagonal. So these two aren't the same. So here we don't have that symmetry. But we do have some things that are the same. Notice that this first row and this first column basically are reproductions of the original elements. So this first row and first column are just copies of the outside row and outside column, right? And so in some ways that R0 is acting like the 1 in this first table. Up in this top table, when I take 1 times something else, I get that thing back. In this bottom table, when I take R0 composed with one of these other operations, I get that operation back. So this R0 is what we call an identity. And up here, 1 is an identity. And you've seen that word a lot. You've had much math, right? So that's a really important similarity. They both have an identity element. How about this? Let's take a look at another one. If I give you in this top table, let's come back up here and let me clean up just a little bit. If I give you one of these elements like -1 or I or -I, can you find an element whose product with one of those, with each of those, gives me 1? So in other words, can you solve this equation? 1 times x equals 1. I times x equals 1. And -I times x equals 1. Is there a solution to each of those equations in that table? Are you saying yes to me, Kyle, or yeah? No, okay. So what times -1 would give me 1? Don't think too deeply, you know the answer to this.
-1.
-1, beautiful. What about I? What times I is 1?
-I.
-I, beautiful. And I won't make you say the last one, Kyle. -I times I is 1. So for each of the things in here, and certainly 1 times 1 is 1. So for each of the elements in this set, there's another element that I can multiply it by to get the identity. Now look down in this bottom table. We hear R0 is the identity. Does this table have that same property? For example, if I take F1, is there something I can multiply by X1 to give me the identity? Yeah, what is that element?
F1 or
F1, yeah, right. You flip it, then flip it back. You're back where you started. So F1 is the solution to this. And I can use some nice notation. What that means is that F1 has an inverse element. So we're going to introduce this idea of inverses. F1's inverse is just F1 because the product of F1 and F1 is the identity element for this collection here. What about R240 inverse? What's the inverse of R240? What times R240 gets you R0?
R120.
R120, exactly. So that's R120. And I'll just write this out because R240 times R120 is the identity element for this collection. Does every single element in this bottom table have an inverse? Yeah, and Sydney, you're saying yeah. So can you maybe like argue why, just like in any way?
I don't know, just based on the fact that you have, like you've demonstrated that a flip and a rotation can get you what you need. There, it seems reasonable that everything in there has one.
It does, but can you give me something? Can we, yeah, that's true. That's all true. It does seem reasonable. But how do I know for a fact that every element in either table has an inverse? So like I go, how do I know F2 has an inverse? And here, let me kind of help. You might not know what I'm looking for. Because if I look at the row for F2, I see that there's something in the top row. I see there's some element up here that gets me back to the identity. So in other words, every single row has R0 in it. Every single column has R0 in it. And that means each element has some pairing that's going to get you back to the original state. Every element has an inverse. Same thing in this top table. Notice there's a 1 in every row and column up there. And there's exactly 1 in every row and every column up there. So there's one last thing that I want to point out here. In this top one, when I multiply any two of those elements together, I get something back in the original set. And the same thing down here in this dihedral, this is called the dihedral group, D3. It's based on a 3-sided figure. Everything down here, when I compose it with something else, gets me back into the set. I can't leave the set. I have closure under my particular operation. Okay. So the things that I'm trying to highlight here are we have closure in each of these examples. We have an identity element and we have inverses in each one of those. And then there's one more thing that's super subtle that like will always remain subtle and challenging for us. So let's take a look at that on the next page, because I was just trying to lead us to our definition of a group. So we take a set G, and this set could be finite or infinite. Everything we've looked at is finite because it gets kind of crazy looking at infinitely many things. And we have a binary operation. So that's like a function on the set G, which we will call multiplication, even if it's not multiplication like we're used to. So back in this thing, I could say, back in this lower table, I could say R240 times FA is FB. And I would just say times, even though I know it's not multiplication. So we're going to use that word just ubiquitously. And so this binary operation, does this notation make sense here with that little cross product? Do you remember seeing that in logic and proof? So this just means ordered pairs. So this is just all the elements of G on one side, and then all the elements of G down here, and we're looking at G cross G. Now that cross, that's not multiplication. That just means ordered pairs. So it really means I'm looking at all the possible ordered pairs. And then I'm applying this operation. So the operation, let's see if I called it star or asterisk or something, takes an ordered pair and produces a single thing. So this is A times B. You could also write this, if I was using that notation, A asterisk B. But in general, we're probably just going to write AB to signify the operation. And honestly, like when I first started taking algebra, I was so naive about all this that sometimes I thought that was at multiplication, and it ended up confusing me a lot. So if I write something like this for our class, that doesn't necessarily mean what it used to mean. It will mean something a little more complicated and deep. And we'll get to that. So this, just being wary, just like a warning sign, there be dragons here. So if I have these things, a set and a binary operation on the set, a way to compose two things and get another one back in the set. So that's the closure. And I also have associativity. This is the thing I didn't talk about because it's a little nebulous. So associativity means this: if I take two things from the set and multiply them, and multiplies in quotes, and then I multiply that result by a third element, I get the exact same thing as if I had multiplied the B and C first and then multiplied the A. So you can do things in different groupings. You can regroup things I shouldn't use the word group. Shit, I can't come up with a good word besides group. Pair. You can do different orders of those things. So associativity, and this must be true for all A, B, and C in the group G. We also have to have an identity element. So the identity element means it doesn't change things when I multiply it by something else. So if I take, and we call it E instead of 1. Sometimes we don't know much about a group besides it's a group. And so we call the identity element E, and we would say that E times A is equal to A times E is equal to A. Doesn't matter what order I do those in. I get back the A, and that's for every element in G. And then finally, there has to be an inverse for each element in the group. So for each A in the group G, there is some B in G such that A times B equals the identity element. And also B times A equals the identity element. Works on both sides. That B we denote by A inverse. So that's just notation. So we could say here A times A inverse is equal to the identity, and A inverse times A is equal to the identity. So can you feel we're lifting off here? You feel, yeah, right? Like we're starting to like pull away from Earth just a little bit. And we're just going to go slow and take it chill, make sure we can, have a stable flight and so forth. Are there any questions about any of that, friends? Awesome. Wonderful. So let's do some simple fun stuff. These tables that we've been looking at, this first table with the I's and the 1s, and then this D3 table, these are tables called Cayley tables. So everything on this page is called a Cayley table. And you learned, this is like one of the first things you learned in grade school math: multiplication tables, addition tables. Those were Cayley tables. You just had operations that are very familiar, but when the operation is abstract and strange, we just call them Cayley tables. But don't, that's all they are, is multiplication table, our times tables. So let's first off note that the order of a group is the cardinality of the set that the group is formed from. So the cardinality just means the number of elements in the group. So back to our original examples, the cardinality of this first one is 4. So this is the order of this group, we call it S, I guess, is 4. And then the order of the dihedral group D3, so the order of D3 is actually 6, because there's 6 total elements in there. So let's start out with chill, like so chill, right? Let's think, can we actually like completely own some of these groups? And this is actually a really famous problem. Figure out how many groups of each order there are. What does that mean? That means I'm going to find a set. I'm going to assume these basic operations hold true. I'm going to assume all these 3 things are holding true for me, and figure out what different Cayley tables I can come up with. So it's almost like, and I can never say the word, like a Sudoku. No, yeah, right. I think Trinity's heard me not say this properly before. What do you say? What do they call it? Sudoku? Oh, okay. Oh, I did it. I learned. Oh, okay, cool. So this is like Sudoku, where we've got to fill in this table, essentially. So group of order 1, you've got to have an identity element. So that means you can't have anything else if your size is 1. Well, that makes life easy. And I won't make anyone tell me what I think is obvious here, that the E times E, the identity times the identity, it has to be something back in the set. So it better be E. So let's just check here. What's the inverse of E? In this little group, what's E inverse? Yes, you said it, Sydney. I saw it. E. Sydney said E. Exactly. Let's just check associativity really quick. So that would mean, this is going to be silly, that E times E times E is the same as E times E times E. Well, that's just, I mean, does that seem pretty clear? Because the only thing anything can ever be is E in this group. So very, very relaxing. So we've got associativity, we've got inverses, and we've got the identity. Rocking. All right, let's go to a group of order 2. So here G, got to have the identity. And I'm going to toss in a second element. So now I've got A. So my Cayley table looks like this. Can you fill that in, please? Are we agreeing on those those identity rows are sweet, right? They're just copies. So there's nothing deep there. What has to go in this last slot? What feels like it has to go in that last slot? What doesn't everybody need an inverse? Right? We have to have an identity in each row and column. Everybody's got to have an inverse. So what's the inverse of A in this group? What would it have to be?
E.
That's perfect. That's it. So this has to be an E here because A needs an inverse. I need to have something times A give me the identity element. That's got to be the case. So the only thing that it could be, well, it can't be E because this already is true because it's the identity. So this has to be A in here. So A times itself has to be the identity element. So you kind of need to look at these properties and get used to kind of piecing them together. But I want to give you a really helpful fact first, and it's a problem in the book that I didn't assign. I just wanted to talk about, and it's going to make Cayley table life so much easier. And you will be making Cayley tables. There is no that is like part of the life of an abstract algebra student, making Cayley tables. So I hope this is moderately pleasing to your math soul. But here's kind of a fact, and I don't want to call it a theorem because I'm not going to do a nice rigorous proof, but it could be a theorem. In a Cayley table, each element of the group, and we're going to kind of prove it, occurs exactly once in each row and column. And knowing that is huge. Like, even if you had known that fact just back a second ago, right? Like, you would have gone, you didn't even have to think super deeply about it. You're like, oh, that row and that column is missing an E. It can't be A because I'm not going to have repeats of any element in that table. So let me prove this to you. Let's say we've got some crazy ass Cayley table. So I've got this element A, and then here I've got B1 and B2, and this thing could be huge. It could be infinite. It's okay. But in this A row, let's say the same element occurred twice. Let's say that there was a C here and then a C here. Are we all together? Like, you know, okay, awesome. So I'm going to write out what that means. Now, usually this, for me, I'm going to try to stick to this. This is the first operation, and then this will be the second. So now, well, so, okay, so that could be a little confusing. So what I mean by this is that B1 times A. So I'm thinking of this in terms of like functions and composition. So when you have functions in composition, they eat from the right. So if I do A first and then B, that means B is kind of eating A to its right, like matrix multiplication, if that makes sense. And that's going to be C. But then I also know that B2 times A is equal to C. So that means that these two things are equal, that B1A is equal to B2A. But I have a group, so everything has an inverse. So there's a thing called A inverse. So, but we have A inverse. It's not in this table. We don't see it. I don't know where it is, but it's in there. So I'm going to multiply on the right here. So right multiply by A inverse. And what I get is B1A times A inverse equals B2A. Notice how I'm grouping those because they were together. So I'm using those parentheses. And I'm being very careful to show that I'm using only the group properties. Right? So those parentheses just mean, hey, we came to the party together. And then A inverse joined in the group. I gotta stop using that word group in like all sorts of ways. But Now, what property could I use to get the A and the A inverse together? Because right now, there's this wall, this parenthetical wall. How could I get A and A inverse next to each other? What property?
Associative.
Associative property allows me to move those yeah, perfect. So the associative property, so I'm going to just kind of bring this back up here. And so now by associativity, this is B1A inverse equals B2A inverse. So I'm reassociating. And what's A times A inverse? E. Yep, perfect. So that's B1E equals B2E. And what does E do when it acts with something else? Nothing, right? It just leaves that same thing. So this says that B1 would have to equal B2. So that means that there can't be two, these can't be different. If I have the same element down here. Now you could do this whole same proof to show it for columns. Can you kind of imagine just like kind of flip this whole argument so that the C's are in a column and then you play the same game? So now we have a really powerful fact that's going to make life really easy for the next table. Let's do this one together. I'm going to give you, so we've got some group operation. We don't know what it is. We've got E, A, B. We've got three elements, E, A, B. Can you fill that table in, please? Now it's Sudoku time. Mini, tiny Sudoku. Oh, shit, man. Damn it. I lost my screen. Lost the screen. You think you got this one rocked out, Kyle? Cool, cool. Let's give everybody a little bit of a chance here. Are there, Kyle, I'll ask you this, are there more than one right answer to this? It's a good question, right? Like, yeah, it's like Sydney and Trinity, don't look. I'm just going to put something up here for Kyle to see and see if he, so he can verify and see if he got this. So yeah, awesome. Good, good. Okay, you can look now if you want. let's talk it through. Let's just talk it through because we're going to do more. Don't worry, you're going to have so much practice with KLA tables. But the first like thing is kind of this big wide open field is like A times A. What are the options? Hey, Kyle, can you talk through maybe, please? Would you mind?
Yeah, so I mean, from the Sudoku perspective of it, which is really how I broke it down. You just look at each of the columns already, and you already have a B in the leftmost and the rightmost column, which just kind of means that it's going to be down the middle. And then you also already have a B in the bottom row, so you know that that B has to go directly in the middle of the table. So that's just what led me to get the B, and then it was just filling in from there, because then you have A, B in the middle row, which leaves the only other option in the middle row to be E on the far right. And then you look down the rows, down the columns rather. And so you have A, B down the middle column. So there's E down at the bottom, and then that leaves A as the last option for the bottom right corner.
Yeah, absolutely. That's solid reasoning. I think in my head I was using slightly different verbiage, but I think that they were basically isomorphic arguments. Is that word isomorphic okay? Math word? It'll be something we talk about here. So a morphism is structure, right? So a morph means structure, and in our class we will talk about homomorphisms and isomorphisms. And an isomorphism just means don't look the same, but actually are the same identically. So I'm saying my thought process was isomorphic to yours, Kyle. Yeah, I don't know. I don't know if there's any other way to really think about that. You know, is there any Trinity, Sydney, anything you want to talk about with this one, or? Yeah. Okay. Cool. So this is kind of, I think I might just make this, here's like a bonus problem. Maybe we should just get the damn homework done first, right? It's like one thing at a time. I was like, but a great problem is how many, so now when we go to groups of order 4, A, B, C, things become a lot more complicated, right? Always the low-hanging fruit. But now the Sudoku becomes way more challenging. And there's not just one right answer. So in everything we've looked at so far, that's it. Here, there's multiple answers. So a fun challenge, and I don't think it's one of the homework problems, but I better check. It should be a homework problem. Maybe the next homework set. Can you find all the possible groups of order 4? And there are more than one. So this is where things start to become crazy. And so then this problem of classify all the groups of each order, order 5, order 6, order 7, you can start to see that this becomes a pretty deep problem and would take a lot of time, and maybe having a computer wouldn't be the worst thing to help with that, right? But people did this long before computers, you know, because you're mathematicians and you just dig doing this kind of stuff. Just real quick, just want to look at this. So now there's only one group of orders 1, 2, and 3. That's it. They all act the same. And let me prove this to you. Let's make a little table and let's look at a solid example just right next to one of these. So let's take a look at the integers mod 3 under addition. So I've got integers mod 3 under addition, and I'm going to say this is my group G. So what would that look like? So here we have plus, good old plus, but it's modular plus, but it's still good old plus. We just mod 3 everything. And then we've got 0, 1, and 2, 0, 1, and 2. If what I said is true, this table should have the exact same rhythm as the EAB table below. Let's, I'll start working on it. You can work on it too. If nothing else, we've got one really easy row and column. So this is all, let's put mod 3 here so that we make sure we got it. And then we got 2. Does that table look like what you'd come up with? Yeah. So check it out. Identity element. is 0. The A corresponds to 1. And the B corresponds to 2. These tables, if I replace those in this table over here, I see that those groups are identical. Even though that first one has no anchor in reality, whatever reality this is up here, Z3 and stuff like that. But that seems more solid. But these two have the same structure. And I'm gonna point out here that these two groups are isomorphic. They are freaking identical. And it's a great word to toss around anyway. As mathematicians, you've got all amazing words. Can you even say onto anymore or hear it without thinking like surjectivity? Right? Like it's just like once you become a mathematician, the world changes in many ways, and nobody can understand but another mathematician. So there's another, quarter 10-cent word or something. No, I don't know. I don't even know what that expression is. My mind was grasping toward the end here. I'm just kind of curious. Did anybody, I saw you working. Did anybody actually fill in this table already? You did. Cool. Can you read off like the next row for me, Kyle? So like the A row, what did you get?
I went BCE after the A.
Yeah.
Then I went, the next one is CEA, and then EAB.
Nice. Very nice. Yeah. Looks good to me. It's got all the things we want. Mostly you just got to check, make sure there's only one of each thing in each row and column, and you're pretty much good to go. So there are four different tables you can come up with, but really only 2 different groups. And that sounds a little weird, but it's because A, B, and C are just arbitrary names for things, right? So there's like really just 2 different rhythms of table you can come up with. Even though with these letters, you could come up with 4 different looking tables. There's really only 2 essentially different tables. Notice here that we have a beautiful symmetry down the diagonal. Yeah. So what that means is that A times B is equal to B times A, and A times C equals C times A, and BA equals AB. This is commutivity. It doesn't matter what order I do the operations in, completely opposite, or not opposite, but completely contrasted with that dihedral group with the triangle. Like that mattered, order mattered there. But here this doesn't. In a group where order doesn't matter, we call that group abelian. So this is an abelian group. Order of ops don't matter. Everything's commutative. Nice, a pretty word. Another beautiful mathy word. So let's see, where are we going next? So what time is it? It's 10:22. Well, let me ask you here. Let's just do a little thinking. I'm going to give you some stuff and you tell me, is this a group? So here, I'm just going to give you a list. Let's play group or not. The worst game show ever. So I'm going to give you a set and an operation. First off, that's standard multiplication there. That's just times. So the integers, standard multiplication. Here's the next one. The integers, the rationals with plus, good old plus, nothing weird. And then the last one I'm going to give you is the integers with subtraction. So first thing, can you find an identity? That would be a great place to look. Do I have an identity element? Then do I have inverses? And then think about associativity. I'm going to run to the restroom really quick, and we'll hit on this when I get back. Better get a separate page here. I just gotta tell you, I'm so happy to be here with you. Like, it's just feeling so good to be doing this. Yeah, it's great. Yeah, it's totally feeling blessed to be able to sit here and just do this stuff with you three today. So thanks for being here. Good stuff. I wish I could find a way to just teach and not have to do any of the other shit that I have to do in my job, because this is like gold. This is the stuff. But then, like, man, I've literally thought about like resigning my full professorship so I could just be like the kind of faculty like Dr. Duvall where you don't have to go to meetings and stuff. Like there's nothing, you get paid less, but there's no bullshit. No expectations of bullshit. Okay, so how about, let's take a look here. How about this first one? Trinity, what do you think on this first one? Is this Z under multiplication a group? Have you got anywhere with that?
I don't think it's a group.
Cool. So yeah, explain. I think I agree.
I don't know exactly like which one failed, but when I was like thinking about it, like I think it's in the inverses, I'm not 100% sure. But when you're like multiplying two integers together, like there's ways when you're trying to like get it back or something that like it ends up being like fractions and not integers anymore. So like
Totally.
There's not like an integer that you can multiply like 6 by or something to like get like something smaller than it, like to get 2. I don't know how to explain it.
Okay, so first off, so you're totally thinking right, but let's clarify your thinking just a little bit. So first off,
Yeah.
what's the identity? Because you need to talk about inverses, you want to know what your identity is.
Mhm.
What's my identity here? What's the integer I can multiply by any other integer and get that integer back?
1.
Solid. Cool. So, and then let's go back to your other example. Let's go to inverses. And this is, you're right, this is exactly where it fails. So what is the inverse of 2? Well, I need to find some integer times 2 that gives me the identity. And this is what you're saying, right? But we can clarify it a little. Once I know that identity, I could just put this example out and I can say there is no inverse. And you just need 1 for 2. What set could I replace Z with to get maybe some inverses in here? So like Z isn't working because I need a half, right? You need a half. So that it's 2 times a half equals 1, right? And then that would be happy. So could I change Z to something else? Yeah, what are you thinking, Kyle? Oh, sorry, Trinity. Sorry, you were stepping in there. Sorry.
You can change it to the reals.
Oh, yeah, that's a bold leap. Absolutely. I was just thinking the rationals, but yeah, hell
too,
yeah. One little caveat. What is 0 inverse? If we go to the reals, let's go to the reals. Why not? I like the reals. What times 0 would give me the identity? It's still 1. Yeah, it's Sydney, what are you thinking?
Nothing.
Yes, no, they can't divide by 0 essentially, right? So like the whole world implodes if we do that. So we would have to go to, and that's actually still a problem for the set that we have, right? There's no inverse for 0, certainly, in any of these sets. But what if we went to the reals and took out 0? And then left multiplication, then everything's going to be hunky-dory. Everybody's got an inverse. Everything is all peachy keen. Toss in another idiotic saying. Cool, good stuff. What about the rationals under addition? This is not a group. Any thoughts on that? So we go through identity. What's my identity here?
Wouldn't it be 0?
Solid, it would, right? It's really important to understand what the operation does, for sure. But the identity here is 0 because you get A plus 0 equals 0 plus A equals A for all rationals Q. Absolutely. What about inverses? So if I have the inverse, what is A inverse if A is a rational? Good. So we don't have multiplication, but you can still think of it as multiplication. So if I wrote this in this set, in this group, this would actually mean A plus B. So that's like the meaning of it. Right? So if I want something, I want to find this element B, which is really just A plus that gives me 0. What would it be? What's the inverse of A?
Negative A.
Negative A, exactly. It's just the opposite. I give you 37/50ths. The opposite of that, the inverse of that is negative 37/50ths, because I add them together and I get my identity element. Is this making sense? Yes, beauty, beauty, beauty. So, and then associativity. Since everything's working so far, we kind of want to address it. We want to make sure that A, B, C equals A, B, C. Why is that true? And translate it. So this means actually this. But we write it cryptically. Is that true? Yeah, that's true, because they're just real numbers and real addition is associative, right? And these are things we take for granted all the time, that you can add numbers in any order and everything's going to be okay. Turns out if you, are anybody here in numerical methods? Who's doing numerical methods? No, Trinity? Yeah, and Kyle. I don't know if Dr. Seibert did it at the beginning, but when you add, like in Python, and you have, not terribly deep precision, you can add numbers in different orders and not get the same result. Did he show you guys that? Yeah, it's a really strange thing, and it's all because of the round off error and all that stuff. And so in a computer, sometimes you can't add in different orders and get the same result, which is really weird and scary. I gotta plug in my iPad here. So we got associativity. So this is a group. Cool. We don't want to make the Cayley table because that would be truly evil. Get this guy plugged in. Shit. Well, that's not it. Where are you, plug? So this last one, what about it? What do we think? Group or not? What's the identity?
Zero?
Yep, solid. Because if I have an integer n and I subtract off 0. Oh, well, wait. So now it's not, I thought that was true too, but now I'm starting to think, do we even have an identity here? Because for an identity, we would need AE equals EA equals A for all the elements. So here that would translate to A minus 0 equals 0 minus A equals A. That ain't true, is it? So we don't have that. So yeah, Sydney, I was on the same page with you. I actually thought we had that and this was going to fail somewhere else. But we don't have an identity because an identity has to be commutative. So that's a really good thing to keep in mind, and that for me as well, that an identity needs to work on either side of things. And this is not true. These are not equal. So we don't even have an identity. It just feels like we do. What about, well, then it's hard to say we have inverses. The thing I was thinking when I came up with this example was it bailed on associativity, because if I have A minus B minus C, that is not the same thing as A minus B minus C, because that negative, right? Because you got to distribute that negative and stuff. So there's no associativity here either. So no identity, no associativity. This is not a group. Interesting. I didn't see that coming. Cool. So friends, this is the game for the next homework assignment. And I'm not going to let you out early, because what I want to do is at least, I want to like make you look at the assignment. while we're here together. So let me actually get the assignment up. I got to pull it off of World Class here. Let's see. So the homework 2 is chapter 2, and this is a smaller assignment. I don't think this is going to be intense. I think that first one had some really hard stuff in it. So it's chapter 2, 4, problems 5, just parts A, B, and C, 13, 15, 20, and 30. And so let's actually go through these together so that your brain, if you don't do this already, I would recommend when you get an assignment in a class like this, just read through the problems. Like right up front, like as soon as humanly possible. Read through the problems. Your mind will keep thinking about them. Like you plant this seed, things are working, and you will be shocked that it will make it easier when you actually come back to do it. So let's do that now. I mean, that's just a good mathematical tip. Probably a good tip for pretty much anything. So let's see. So number 4 is pretty straightforward. You're given a bunch of sets. Does everybody have their book with them or some? No. I'm sorry. I don't know. Can you? Okay. So Kyle. So can you even read? It's a little out of focus, but they give you those 4 sets, and they add. Ooh, it's starting to kind of come in to play. Which of those sets are closed under the operation? So this first one's just like which of those things are closed under the operation, and they're just modular arithmetic there. So it's addition or multiplication, mod, whatever. So see if you're closed. One way to do that is make a Cayley table, right? And that, so for example, part D, so number 4D, I've got this set 1, 4, 5, 7, and then it's mod 9. And I could just make myself a Cayley table. And if I get something that's not 1, 4, or 5, or 7, mod 9, then it's not closed, right? So that's just a nice straight way to approach that problem. I think an organized way. Let's see, number 5. Number 5. In each case, find the inverse of the element under the given operation. So for example, and there's a group we need to talk about here. The first one is 13 in Z20. So now, first off, there's an unspoken here. Notice there's no operation. When you're just given a modular group like this, like Z20 or Z whatever, the unspoken operation is addition. So you need to identify the identity element and then figure out what the inverse of 13 would be in this group under addition. You can maybe do it in your head if you think about it just a little bit. Now, part B, and we've got just enough time here. I'm going to show you this one real quick. This is 13 in U14. All right, let's talk about these U groups really quick. I'm really glad we're going through this because this could have been intense. So UN, this is a whole collection, an infinite collection of groups, is equal to, first off, all integers relatively prime to n and less than n. And the operation, all positive integers, sorry. And the operation is multiplication, mod n. So let me give you an example here. So like, let's say I had U8. So I go through and I think all the numbers that don't share any common factors with 8 are going to be in this set. And 1's always going to be in there. That'll be your identity. 2, no, 2 and 8 share a factor. 3 can't be 4 because 4 and 8 share 4 is a factor. 5 and 7. So that's U8. And these can get pretty intense. So like the one you had was U14. So you'll have to kind of like think about what that is. But you can make a Cayley table. For these, and you're just going to go through and do that multiplication. So for example, let me do like the most extreme thing I can think of, 7 times 7. So that's 49, and then I take that mod 8, and let's see, so that's going to be 1, right? So 49 mod 1 is 1. Does that make sense? Because 6 times 8 is 48. You got 1 left over, so I got a 1 there. So now I know that the inverse of 7 is 7 in this group. And that's kind of how you'll need to proceed with that problem. And we're pretty much out of time. I don't want to run over, but at least we got kind of a start on this. So what I'm begging of you is to please read through the rest of these questions and put a little bit in before Monday. And then, because I'd love to like just start off the day with talk about questions. Yeah, sound good? Because I'm going to be a hard ass. I'm going to be a super hard ass and not extend this homework date to keep us moving. We're going to move. So I'm just like, that's as bad an ass as I can be. And I even feel bad about it, but whatever. Got to be kind of a coach. So thank you, friends. Thanks for showing up. And I will shoot me emails. Anything you're confused about a question, email me, and then I'll email the group and let everybody know. And other than that, I really hope to see you on Monday. It's the plan. So, all right. Bye.
Perfect. Thank you.
Thank you. Thanks. Oh, Trinity. Oh, shit. Yeah, good. You're still here. Yeah. Let me stop recording. I reached out to